Hey, good morning, everyone. My name is Adnan, and I'm one of your room hosts. Just some important housekeeping information to share. Emergency exits are located at the back to your left. Restrooms are located at the back to your right. Just remember to silence all your devices during the session, and please remember to provide feedback after the session as well. For this session, running containers in a hybrid environment, please welcome to the stage Harsha Nipani and Lata Nagaraj.
All right, good morning, everyone. All right, welcome to this session. This is running containers in a hybrid environment. The goal of this session is, this is, by the way, a 300-level session. I'm assuming you have a background on containers and how to write Docker files and Docker images. So we're not going to go dive deep into that aspect. We're going to be looking at patterns on how do you deploy containers using AWS services. So here's the agenda. I'd like to focus on the ECS and Fargate implementation. That is a method of orchestrating containers on AWS. And also, we're going to touch a little bit about what are Docker images, why Docker images, and then the use case of Fargate, and maybe touch a little bit on EKS as well for folks who are using Kubernetes. And finally, in the final segment, Lata, who is senior principal architect, application architect with FINRA, she's going to walk us through the journey that FINRA has taken in terms of adopting native services for cloud orchestration. All right, containers and Docker. One of the fundamental issues we have heard from customers is we have, again, now monolithic applications. Monolithic applications, the problem with those is when you are trying to do a CI/CD implementation to essentially for faster time to market and things like that, the main problem is because those are tightly coupled components in a monolithic application, the time to market and time to deploy is sometimes months or more, right? To break down that cycle to help implement faster iterative development, the primary driver here is faster time to market, agility, and speed, right? Speed of deployments in a CI/CD cycle. That's how the trend has been for the last few years. And containers is not new. We have, in the past, we have seen BSD jails. We have seen Solaris containers. And then the next evolution has been with the Docker containers. The whole idea is the problem that Docker containers is trying to solve is you have all these different operating environments, meaning a developer builds a code, tests it on a laptop, and then goes to, say, or your integrated development environment, and then moves into development cycle where if there are environmental mismatch, meaning configuration drift in terms of libraries or dependencies and things like that, the code he or she has developed may not work consistently across the environments. That's the biggest problem with the CI/CD pipeline of leveraging monolithic applications. That is where Docker comes into play. But also, just to highlight some of the issues you have with respect to different environment is, when you are developing code, it is also important that it be portable, right? And also consistent in terms of performance metrics, and so in terms of operations and things like that. That is the whole idea of moving towards microservices, and Docker has been a champion in that space, right? Docker gives you the ability to the developers to deliver code using containers where all the dependencies, like when I say dependencies, it is something like operating environment, for example, runtime environment for your application code, and any libraries that are required to compile the code and things like that are packaged in a unit of delivery, and that's what containers are all about. It's lightweight. Unlike virtual machine-based applications where you have to have an instantiation of your operating system and all the device drivers and things like that, you don't necessarily have to have all those the VM-based deployments with Docker. So to give you, again, another perspective is when I say self-contained, you are essentially defining the kernel, you are defining the base image that goes into it, and then all the dependencies. So for example, here in the stack, we're highlighting you have the Node.js image and then an Nginx image. Those two are packaged, and then you have a container, a space to write container code, right? So you're packaging all this into a Docker file, and you deploy the Docker file into containers. So that becomes your core image, and that's immutable. When I say immutable, again, once you create your Docker image and you publish the Docker image, you don't have to worry about the operating environment being changed, right? So why virtual machines versus containers? Let's take a step back. Again, like I told you, with the VM-based deployment, the biggest issue is for folks who have managed either VMware or maybe go past 10 years, 15 years ago, there used to be Solaris containers. The issue with that is every single application, you're essentially taking a bare metal server, you have a hypervisor layer on top of that, and on top of that is your instance of the operating system in which you're running an app. So there is a OS instance for every single app. So there is no partitioning at the process logic layer. It is partitioning at the hardware layer. That's the main difference. What containers gives you, again, as you can see here, for the VMs, there is a guest OS element. So you have to maintain the operating system patch, packages, and things like that. Whereas on the container model, it's very lightweight. You're just maintaining one host OS. On top of that is your Docker operating environment. So lightweight, very portable, easy to manage. And that's the whole goal of microservices deployment using containers. So again, packaging application code. So you know the dependencies. As a developer, you would know what dependencies are there in terms of your code. And it's easy to reproduce that code. And also, it's immutable. Like I said, once you package it with all the dependencies in the Docker file, you know that it will consistently run across the environments. And it's portable. So how can AWS help in this domain of containers? If you are a large enterprise customer, or even, for that matter, a startup, the challenge that you are going to face is as you start developing multiple applications in microservices, a scheme of things where short burst cycles in terms of deployment and also faster development cycles, you may have multiple microservices managed by what we call two pizza teams, right? Like short, small dev teams managing a small component. Just manage one component and do it right and scale according to the demands of the workflow or the business. The challenge becomes if you look at the enterprise-wide applications, you could potentially end up with thousands of containers, and then orchestrating and managing those could be a problem. That is where AWS helps you with the orchestration. So you can continue to operate Docker containers on AWS as you would on-prem, where the value add or the value prop comes into play is how do you manage these, how do you orchestrate these. That's where we are talking about these different services. So let's start thinking about a CI/CD cycle. So you build the Docker file. You have to push the Docker file into a repository, right? A managed repository. That's where the ECR comes into play. ECR is the container registry. It's a fully managed Docker registry by AWS. So you don't have to worry about scaling, high availability, and things like that, and also durability. Those are the things that are out of the box. So you push that code into the registry. Now you have to spin your containers on top of that, right? Using those images. So that is where the hosting piece comes into play. There are two variations in terms of hosting. Either you can provision your EC2 instances as you would normally do with VMs and subscribe those into the container services for orchestration, or there is a Fargate option where automatic provisioning of these EC2 instances are taken care of by AWS. And then finally, the orchestration layer itself. You have ECS, Elastic Container Service. That is a managed service to manage your Docker containers and the operating environment for the clusters and things like that. And for folks who are familiar with Kubernetes, Kubernetes is another orchestration layer. This was developed by Google. If you're familiar with Kubernetes and you want to use that, instead of ECS, you can use EKS, which will help you essentially manage Kubernetes deployments. All right, let's touch a little bit on ECR. Again, going back to my CI/CD discussion, so you create your Docker files, you register those, and essentially push those into ECR. Why do you need to do that? That becomes your central repo in terms of your code deployments, right? The pipeline orchestration itself, you can do with either AWS code services like code commit and code deploy, or third-party services like Jenkins in terms of pipeline management. But essentially, this is your central place where you register your Docker images. Why is it important for you to consider this? Because again, it has native integration with Docker, so all your Docker toolset, the commands that you're used to, is fully compatible with ECR. And highly scalable and highly available. So underneath the covers, ECR uses S3 to save your images in an encrypted fashion. So first of all, you have encryption of all your Docker images. Next, security, again, from an enterprise customer standpoint, from an InfoSec standpoint, how do you manage these registries? How do you manage I want only my dev team A have access to their images? You can do that with permission control using IAM. And from a resiliency perspective, your images are all stored on S3. And for the folks who know S3, it has 11 nines of durability. And whenever you do a put operation against S3, it is stored in 3 different availability zones. So if you have an AZ problem in within a region, it is still durable with 2 other images. And then I did mention, in terms of security, all your images are encrypted, but also important to take away is from an auditability perspective. A lot of times customers run into this audit compliance requirements, be it FISMA or NIST or PCI DSS. Those can be satisfied by making sure all these API actions are logged in CloudTrail. All right, evolution of compute. When I say evolution of compute on AWS, I mean in the context of running containers. So before the launch of ECS, we heard customers running Docker containers directly on EC2. That caused a lot of issues for customers at scale, because now, as I told you, running containers at scale is a challenge in terms of manageability. So we launched the ECS service, and the whole idea is to give you that orchestration layer. So with ECS, you have 2 launch types, as I mentioned earlier. One is EC2 launch type, ECS with EC2, meaning you're provisioning EC2 instances and registering that with ECS. The other one is AWS Fargate, which is essentially, again, container orchestration, but you don't have to provision the EC2 instances. We do it for you based on your definitions. So just to give you a few constructs about how this all works, so you essentially provide resources through EC2 or Fargate, and then you run tasks on top of those. And tasks are basically a logical grouping of containers for a specific workload or a specific microservice. Let's go one step deeper. Just to draw your attention, what goes into this is you have these EC2 instances, right? These are EC2 clusters. You provision those clusters and register with the ECS. The way these clusters interact with ECS is through an ECS agent, similar to how you have a Docker daemon running on top of EC2 instance. These ECS agents, the core functionality of ECS agents is to interact with the control plane APIs of the ECS service itself. So the control plane interactions with your EC2 instances is what ECS does. Why is that important? Because any API action, like creating cluster, managing cluster deployment of tasks on top of a container, how do you know whether the container is healthy or not? Or how do you, and there may be situations where you want to auto-scale your tasks, All these API interactions are handled through that API function, which essentially talks to your ECS agent. And then you have the construct of the task itself, as you can see there. So task, as I told you, is a logical grouping of your containers for specific workload. In our case, you would be talking about maybe chop down your monolithic into microservices. That one microservice component can consist of a task with multiple containers in it. Cluster management, again, placement service. There may be mechanisms. For example, all microservices are not made equal. If you think about your UI or logic layer or things like that, when you're processing a web form, maybe for the logic layer needs more compute power than the web form, right? So containers may have different operating requirements. So to make sure those task placements are done with the right kind of instances and right kind of CPUs, and also maybe give you more resiliency like multi-AZ and things like that, that task placement is also extremely important for resiliency and for performance reasons. So for that, cluster management engine is essentially your go-to component. And then, of course, there are two mechanisms. One is run container by itself, like a batch operation. You're crunching data. You're doing some financial transactions, like maybe Monte Carlo simulations on a large scale of data set that's coming from S3. Or there could be a service that is always running, and you want to expose this service to an external-facing web app, right? So for situations for like those, you may have a load balancer component where you register your service and inject data from your load balancer. And by the way, that doesn't have to be exposed to internet. You can also have internal-facing load balancers too, like private ones. The constructs of ECS, just to highlight some of the most important ones here: task definitions, where you register your requirements to run all your application data, right? Like the image, what's the CPU memory requirements, and things like that. And then once you create, so first is you do that task definition, you push that task definition to your registry that we spoke about in ECR, and then you are going to create a cluster. Cluster is, again, a combination of your EC2 instances, and you have two choices. One is, if you want to do a one-time execution of a job, like a batch job, processing workloads, you would do a run task, right? And that run task is nothing but an instantiation of the task definition that you have defined. Or in scenarios where it's not one-time job, I have a continuously running application like a web app. In a situation like that, you would want to create a service, register that service with the load balancer, and ingest traffic to the service itself. All right, so we discussed containers, we discussed tasks. Now, what's the problem is, as you have heard from a lot of AWS folks, and even in our blog post, we talk about you need to be multi-AZ deployed, and you need to do scaling using auto-scaling groups and things like that. So as you scale out, as you start these multi-AZ deployments, it gets incredibly difficult to manage all these tasks, right? Routing tasks, routing traffic to specific tasks and things like that. So that is where the key takeaway from an orchestration and scheduling perspective, that's where the ECS service gives you. So key takeaway for you guys would be this, is first of all, you can run your tasks in VPC mode, meaning it's all if you choose to do so, you can run this in your RFC 1918 space, that is private subnets. These are non-routable IP ranges, so it's only available internally. But if you choose to expose that into a public subnet, that's OK too, right? Advanced task placement, I told you about that. There are just some dive deep topics on that. I'm not going to cover that here, but there are tons of documentation on that. Strategies for enterprise customers, how to orchestrate the task placement. Deep integration with AWS services, I just spoke about ECR and load balancer and S3, and maybe your containers want to talk to databases or talk to DynamoDB or Aurora Postgres and things like that. So that's you have native integrations right there. Powerful scheduling engines, again, that's where the scheduling algorithms, you can take full advantage of that. And finally, of course, the monitoring piece itself. Similar to, so we discussed about the orchestration ECS does. The only problem with that approach is somebody has to manage the resource allocation. If you're running out of, say, for example, you are expecting X traffic, and you got 10X traffic or 100X traffic. Now you're auto-scaling based on your auto-scaling configuration. But then there has to be underlying compute to support that auto-scaling needs. And if you don't have it, or you did not provision it and register with ECS, you are going to have performance degradation because you don't have compute to scale. So to solve that problem, and also in addition to that, there is also patching, packages, and package updates and things like that your regulatory requirements forces you to do. And you have to constantly update your base AMI and customize it to your corporate needs, and then spin up EC2 instances. To avoid that problem, we have launched AWS Fargate, where you as the customer can just focus on your microservices deployment and not worry about ECS clusters, meaning provisioning of clusters. We will take care of that based on the task definitions that you have defined. The only caveat is if you're doing any machine learning modeling using containers. I've seen customers doing that. Fargate doesn't support GPU-based instances yet, so that's on the roadmap. That's something that we'll be looking into. So if you have a machine learning requirement that has to use GPU instances, Fargate may not be suitable at the moment. That's something on the roadmap. No clusters to manage. Underlying infrastructure is automatically taken care of, meaning if there is a hypervisor failure and the VM dies, AWS automatically provisions another instance for you. The constructs of Fargate is not different from ECS EC2 model. It is the exact same thing. You would register your task definition, push it to ECR, and then use during the launch of the cluster, you would say, instead of saying ECS EC2 launch type, you would say ECS with Fargate launch type. So that's the only difference between the two. All right, a little bit about networking. This is also extremely important for you to understand from a performance reasons. First of all, there is 3 different models. The host networking mode, which nobody uses anymore, but bridge networking mode is important. This construct itself is important. So for example, if your container C1 is running inside this AWS instance, as I told you, on top of the AWS instance is your Docker container. Inside the Docker container is actually your application code running, right? When you want to egress or ingress out of that container, right, receiving traffic, sending traffic, and things like that, what happens is all your hypercalls are the device driver calls to your network interface card, right? All those hypercalls go through something called a Docker Zero bridge, right? And the Docker Zero bridge leverages host's ETH0 interface. So the host itself has a networking interface, and Docker Zero Bridge is the conduit between your container and the network interface card. So all the routing takes place through that interface. You don't, as a container, you don't have direct access to your network interface. It's via the Docker Zero Bridge. And then you have the second container, say you have another container running in Docker in the same cluster. And if you have to talk to container 1 needs to talk to container 2, there is no direct interface connection between the two. It has to traverse through the Docker Zero Bridge. So that's how bridge networking mode works. It is essentially relying on the constructs of the Docker daemon itself using Docker Zero Bridge. So why is that a problem? For some customers, well, again, local traffic must transit through ETH0. And why is that a problem? If you take a look at that, what happens if the hypervisor fails? So essentially, the ETH0 interface could be an issue, right? Or if there is a performance problem, then it's going to affect multiple containers. And traffic between containers with the same task, within the same task workspace has to transit through the Docker Zero Bridge, right? There is no one-to-one mapping on there. So to solve some of those issues, some of the feedback that we received from the customers is, well, if we are using the ETH0, the problem is now if container 1 needs to talk to S3 and container 2 needs to talk to database, I have to give NACLs and security group permissions to both, right? So that's the problem with that approach. So what we did is we launched AWS VPC networking mode as a new method of networking within the container namespace. Here, what we are doing now is, instead of going through the ETH0 interface of the host itself, we are leveraging we're essentially leveraging VPC integration through the ENI. And we are spinning an ENI. We will be using your private subnets as part of the provisioning process so that you can actually see your ENI being consumed. And we will use that ENI to have task-level networking. The advantage of this this approach is you can do that isolation at the task level, not at the host level, right? So that's the key takeaway for you. All right, with that, and also some more enhancements. Before task roles were introduced, one of the challenges that we saw with customers' use cases is task 1 needs to talk to DynamoDB, task 2 needs to talk to S3, but then they all are relying on the EC2 instance role. So you have to give more permissions to instance role. What is that? Why is that a problem? Because now task 1 also has access to S3. Why? Because you now said S3 allow at the EC2 instance role level. So it's a security loophole if you think about it. So to address that problem, meaning task 1 should not get access to S3, what we have introduced is task roles. So now you can isolate, give granular IAM permissions to tasks for the processing that it needs to do. All right, reference architecture. I won't take too much time here. Just to give you an overview here, you have private subnet. Your tasks are running in the private subnet. If it has to egress out, a common pattern we have seen is using your NAT gateway so that you're not exposing it directly to the internet because it's all private subnet range. And you can see with the quad 0 on the route table, all your quad 0 traffic traverses through NAT gateway, and as you know, it is a managed AWS service, so you don't have to worry about that one. In a scenario where you're exposing like a port 80 or something like that to internet, you can do that through load balancer. Essentially, you're ingressing from internet into the public IP range through a load balancer. You can do port translation from that to that, and your Fargate tasks will respond to the traffic. So that's another. The reference architecture for, so just to call out some of this is essentially a task definition. There's a bunch of documentation online to see how to spin up these resources. And this is a reference architecture on how this works. A lot of visibility tools and a lot of integration. So just to give you a recap, we just talked about AWS ECS, Fargate, and ECR, and there are tons of other integration with other AWS services. So how are customers using ECS or container services on AWS? To walk us through that next segment, I'd welcome on stage Lata Nagaraj from FINRA.
Thank you, Harsha. Welcome again to the session. My name is Lata. I'm architect at FINRA, primarily focusing on DevOps products. I'm very excited to be back again this year and to share with you some of the experiences and the lessons that we learned in our container migration journey. A little bit of introduction of who we are. Most of you who are in the financial domain would have already heard of us. FINRA stands for Financial Industry Regulatory Authority. We primarily regulate broker-dealers and market exchanges. In short, we regulate the stock market. And our mission is to protect investors and to promote market integrity. A little bit of statistics on the volume that we deal with. We currently regulate about 12 market exchanges, oversee more than 3,800 firms, and monitor about 634,000 broker-dealers currently working in the US. So we are essentially a big data processing company, and on an average in a day, we have about 135 billion events that get ingested into our system to be processed for surveillance. When we reconstruct and replay these events to analyze, we land up with more than trillions of nodes and edges. That kind of gives you an idea of the complexity of data that we are dealing with. And we also store a large amount of data, which is about 30 petabytes currently. And to replay and analyze this market data, we use about 50,000 compute nodes on an average per day. And currently on AWS, we have about 150 applications running and helping us achieve our mission. All right, so before we started our container migration journey, we had to deal with two categories of apps based on their infrastructure need. One, the on-premise data center legacy applications, and the other set of apps which we already moved to AWS cloud, but they were using the traditional EC2 ELB model. And each category of these applications had their own set of problems. Like on-premise, we were constantly battling with infrastructure costs, and we did not have the dynamic scalability of our infrastructure based on our application load, and we had long release cycles spanning across months, which prevented us from going to the market faster. And this entire process, we did not have the speed and agility that we wanted. And dependency management was also quite complex, where if you had needed certain application packages to be installed, it was either done through semi-automated scripts or manually sometimes. And we also lacked environment parity. So most of the times was spent in analyzing issues which did not surface on a lower environment, but you landed up having that on prod, and this was mainly because of not having environment parity. On AWS, the costs did reduce, but we still saw that it started increasing as we deployed more and more microservices onto the cloud, because each microservice now needed its own auto-scaling group and load balancer, and with the volume that we were looking at, it was not going to scale. And we also had to deal with slow build and deploy time. So for example, if you have to deploy your application, your EC2 instance probably has to be configured with certain packages that your application depends on, and you could probably automate it using automation tools like Puppet, but still we saw that the deployment time in some cases span from 30 minutes to 45 minutes, which is pretty high. And lastly, we still had to address the parity issue, which we had even on the on-premise applications. So what we saw was we could address all these problems by using containers, and we saw that it mainly had 5 benefits. The first one was it was easily portable. Now my application was packaged as a container, and it was more or less a sandbox runtime environment, and I could easily drop this container on any host and have it running. So it was very easily portable. Second, it was very cost efficient. Now, instead of having one auto-scaling group and ELB for every microservice, I could fit in multiple of these containers onto same host. Thus, I could use my compute to its maximum efficiency. And all this was way faster, so I did not have to deal with any more of long deploy times that we had in the EC2 ELB world. The building and deploying these containers was very fast. It was probably brought down to like a couple of minutes now. This was mainly because we used a Docker layer caching, and we had certain base images which packaged all the common dependencies that applications needed. And my application image could just extend one of these base images and only focus on packaging what was required for my app, which is mostly my application code. And the productivity was also increased. This was mainly because we had environment parity now. Once the Docker image was built and tagged, it was pretty immutable, and the same tagged image could be used and deployed on different environments. So we did not have to battle with any more of environment parity issues. And lastly, we achieved all this having a simple and lightweight solution. So my application would now just have to deal with a Docker file, which defined the dependencies that it needed or configured, and a Docker Compose file, which defined the containers that made up my application and the relationship that they had with each other. So it was very simple and lightweight. So once we identified containers as a solution, the next logical question was, how do we manage these containers? We did not want to have our own container management solution, and that's when we looked at what AWS has to offer. And when we started our journey, it was pretty much ECS with EC2 launch type that was available. Later on, EKS and Fargate came along. So in the subsequent slides, we'll see how each of these services compares to one another. So let's start with ECS. So when I say ECS, I'm referring to the EC2 launch type. So the pros are, it is very simple and easy to get started. So the learning curve for EC2 launch type is very simple and very low. And it also integrates very well with your other AWS services like your IAM, your load balancers, and so on. The cons, with simplicity comes the lack of flexibility of having more fine-grained placement strategies if you compare it to like services like EKS. And also you have to deal with the cluster scaling overheads. So it is completely your responsibility now as to how you define your scaling events to expand and shrink based on your application node. And you also have to periodically update your AMIs on your EC2 instances to make sure that you're up to date with your security patches. So these are all the overheads that you have to deal with the EC2 launch type. So the use cases, it fits very well when you want to run any kind of batch jobs, standalone tasks, or web applications, which could be your UI, APIs, and microservices. Now let's see how Fargate plays out. So Fargate is a serverless option, and as compared to EC2 launch type, you don't have to deal with any more of your cluster scaling overheads. Fargate takes care of it for you, and no longer you have to do any kind of AMI updates to be in sync. So all those overheads are eliminated with Fargate. The cons, it's currently lacking the encrypted storage support, which is a big deal for us at FINRA being a regulatory firm. And also it does not offer EFS integration, which is the Elastic File System integration. So if any of your applications have necessity to share certain content on EFS, then Fargate might not be an option. And since Fargate uses the AWS VPC mode for its networking, it assigns the ENI per task, which means you have to be cognizant of account level, account region level ENI limits. Use cases, it's pretty much very similar to ECS. It works very well for web apps, standalone tasks and batch jobs, or any stateless application which can manage its states externally using S3, RDS, or Dynamo. Now let's look how EKS plays. So EKS, which is the Kubernetes service provided by AWS, it provides you more flexibility in terms of your container placement strategies as compared to ECS. And it also has a very large open source ecosystem, so things move faster over there. The cons are the learning curve is very high, and cluster management is also pretty complex when it comes to EKS. So you will spend quite a lot of engineering effort to maintain these clusters as compared to the other services. Use cases, EKS is like, it's very good for applications, especially if you want to run it in a hybrid mode, or you do not want to be tied to a specific cloud provider, or you have a combination where you want to run an app both on-premise and on the cloud. So it plays out very well for these kind of use cases. And we have also seen that EKS is a very good candidate for big data processing, especially with frameworks like Spark coming up with support for Kubernetes by intrinsically. So it's a good fit for big data processing as well. And many of platform applications, mainly COTS apps, now come with a default support for Kubernetes. So EKS is lucrative even for those kind of applications. All right, so when we compared all these three services, we chose to go with ECS with EC2 launch type, primarily because it was simple and easy to use, and it was a good fit for majority of our use cases. And it was easy for us to migrate from our EC2 ELB model to ECS ALB model. And we went with the approach of having cluster per business domain so that we could avoid, to a certain extent, cluster management overheads. We definitely want to be on Fargate in the future, but the lack of encrypted storage is what's preventing us from going to Fargate. So EC2 launch type is our solution for now. All right, so once we had the container and container management service identified, then it was how do we really do the migration? And we had to deal with 6 major challenges. The first most important one is the volume of enterprise apps that we had to move. And the security and compliance aspect that we wanted to integrate into our continuous delivery pipeline seamlessly rather than having it as an afterthought during our release process. So all this needed the right automation and tooling to be put in place, which would have best practices embedded within it and also have the desired architecture incorporated in it so that apps could easily move into the container world. And lastly, the rollout strategy, basically training our developers and getting them up to speed to have them move to containers. So we will see how we addressed each of these challenges in the subsequent slides. Let's start with the desired architecture. So we wanted our clients to hit the different endpoints, basically your UI, APIs, and so on, through a load balancer. We chose to go with application load balancer because it's a layer 7 load balancer, which provides you more advanced routing capabilities, like you could do host-based routing or path-based routing or a combination of both. And it also gives you flexibility to route your traffic to specific target groups, which internally maps to your a group of containers forming your ECS service. So ALB front faces your ECS cluster, which is underneath an auto-scaling group of multiple EC2 instances. And our images were stored on ECR, the application Docker images, as well as the base images. Now, once you have your auto-scaling group set up, you can deploy different kinds of applications, different flavors of applications, all going onto the same cluster. So you could have a Spring Boot microservice, your Angular app, or your monolithic app, all sitting on the same cluster. So if you see, there is a pattern to each of these applications. It is underneath ECS service, which is running n copies of your tasks. And each task is a group of containers that is making up your app. You see that all of them have an identity gateway, which is a container that takes care of authentication and authorization for your application. And it acts as a reverse proxy and routes your traffic only if you're authenticated to your application container. And we also went with the approach of having a sidecar for our logging needs, basically a Splunk sidecar. This was a solution chosen because this would work both for EC2 launch type as well as our Fargate launch type in the future. And as we discussed, ALB would now take care of routing traffic to each of these ECS services based on different path and host name routing options. And on the EC2 host, we have CollectD, which is an open source utility that helps us gather different metrics like CPU, memory, disk space, and so on. And this helps with the teams to identify, to profile their applications and to determine how the scaling policies should be. And lastly, we ensured that all the EC2 instances that were launched were evenly distributed across different availability zones to be highly resilient and to have better throughput. Okay, so now let's look at AMI. So the EC2 instances that run the AMI, they use the FINRA ECS optimized AMI, which is basically an extension of Amazon's ECS optimized AMI. But on top of that, we added certain security implementations, like we have CIS security specification for Docker implemented, and we also have security scanning for containers using Cloud Passage Halo agent. So let's now look at the Docker images. So we went with the approach of having certain base images for different flavors of our apps. So these base images were now reusable and compliant, and app images would extend from any of these base images based on what kind of app it is, and they would only focus on packaging their code and configuration. So this was very easy for us to scale, because as an application developer, I would not require to be cognizant of any of the security or compliance related issues, and I can just focus on having my application code in there. Okay, all right, so now let's move on to infrastructure automation. So we have a tool by name Provision, which is basically a wrapper around CloudFormation and AWS SDK APIs and ECS CLI if you want to create your ECS-Task definitions from Docker Compose. And it also comes with the best practices integrated into it. So when I say best practices, for example, it comes with certain defaults, so you don't have to configure every possible property for your infrastructure, but you could go with the defaults and just have your specific configuration on top of it. It also comes with security and compliance inbuilt. So for example, it will ensure that your ALBs always have secure listeners, and it has the right ACM cert applied on it, and so on. Or if you're creating an RDS instance, it makes sure that your encryption is always turned on by default, and so on. It also wraps around other FINRA-specific tools and libraries, like we use Fidelius, which is an open source utility that helps with secrets management, and it wraps around DNS APIs, which is our way of handling DNS names internally. So using this tool, you can now create multiple stacks, like you can create your ECS stack, which underneath is auto-scaling group. You could create your ALB stack, where it would create your secure listeners and set up a default target group for you, create your repos for different applications, and a service stack which would have your task definition, target groups, and routing rules accordingly. So let's look at the delivery pipeline. So we have a specific delivery pipeline for your ECS cluster, which takes care of creating the cluster, updating your cluster. You would use it for any AMI updates or changing your launch configuration for your auto-scaling group and so on. So as you can see, the infrastructure is defined as code and built and pushed once to your S3, and from there on, it's the same infrastructure code that is used to create your resources on each of the AWS accounts across your SDLC. We have another pipeline for ALB, so we would typically have one ALB per ECS cluster, and the pipeline is very similar to what we saw for ECS, and you would use this pipeline for updating anything on your ALB, including assigning additional DNS names to your load balancer. Lastly, you could have multiple app or service pipelines, which would, for each of your ECS service or component that you're deploying. So methodology is still the same. You build your app code and your infrastructure code once, and here you additionally also package it into a Docker image zip, which gets pushed onto S3, and that zip is what gets promoted across your different AWS accounts. And you use provision tool to pull the image from S3 and then push it onto ECR and then provision your ECS service. So we build and tag the Docker containers once, and we push and deploy the same container to any account multiple times. So a little bit on the production metrics here. We have about 100 plus clusters currently with more than 200 plus EC2 instances, and we have about 300 plus ECS services mapping to around 500 plus active tasks currently running on production. Okay, so some deployment strategies. So different apps have used different deployment strategies. Some applications have gone for blue-green deployment, where you have your current version, which is your blue stack, and then you bring up another parallel stack, which is your green version. And once you're satisfied with the newer version, what you do is you switch the two. So you could switch that by using ALB DNS switch, or you could do that with the target groups switch. So blue-green deployment is very less risky as compared to others because you have two parallel environments, but it may not be suitable for applications where the database wouldn't support two different versions running at the same time, so it might not work well for those kind of applications. The other deployment strategy is the zero downtime deployment, which is basically a rolling update. So here your ECS service takes care of pulling down the older container versions and registering newer versions by rolling them based on your minimum and maximum healthy instances that you define. So some of the best practices, it is very important that your cluster is right-sized. So you profile your application and gather the metrics and learn how you want it to scale based upon the peak load that your application have to deal. So you need to do that both for your cluster as well as your ECS service. And also it is very important to spread your tasks both across availability zone for high availability and across different instances by using placement constraints. And lastly, logging and monitoring is very important. You do not want to be blinded if there is any issue on your app. You definitely need logging so that you can analyze the issue better, and monitoring to be alerted if there is anything going down. So the future is very exciting. We want to catch up with the serverless wave, and Fargate is definitely one of the major candidates over there that we are looking at. And we want to use EKS for many big data processing applications. So EKS adoption is in the pipeline. And we want to open source the provision tool by end of this year so that other organizations can also use this tool and plug in their own security and compliance needs and get their infrastructure set up more easily. All right, so we have a lot of other open source tools too. So if you go to technology.finra.org, you will see what's currently available. To start with, we have Gatekeeper. So this tool is very handy if you have a burning production issue and you have to get onto your EC2 instance or log into your RDS instance to analyze the issue better. Then Gatekeeper helps you with temporary access to these instances. with, of course, an audit trail of who requested it and when was the access granted and so on. And we have the Yum Nginx API, which helps you manage your RPMs on Yum. And Aphelion, which is a dashboard application which helps you visualize your AWS service limits and alerts you if you're reaching any of those limits so that you can take care of it beforehand. And recently, we open sourced Fidelius, which is a secrets management tool. It comes with a web app, a pretty UI, which will help developers to manage their credentials on their lower environment, and ops to manage credentials on the higher environment. And it also offers SDK APIs for automation needs for if your application needs to pull in secrets at runtime. So coming soon, we already spoke about provision tools, so that's by end of the year. And we also have another tool called CloudPass, which issues temporary tokens using the STS service. So that's also in the pipeline. And lastly, we have Portis, which helps you with managing your security groups based on certain security policies put in place. So I highly encourage all of you to take a look at our open source tools and see if it would be useful for any of your needs, and also we welcome contributions. With that, I think we come to the end of this session. We are running out of time, so we will be out there, me and Harsha, to answer any of your questions that you might have. Thank you so much.
Thank you.